order dynamics, particularly what you might typically see out of a range of circuits that you'd have resistors, capacitors, and inductors in it. And these kinds of structures are certainly some very familiar forms. These might be slightly less familiar forms, but there's still many different ways to get L, R, and C kinds of circuits that give you second order dynamics. Okay, so we have just one of each of these elements. They could have come from all sorts of places. We could have combined things. All of that would work well. So this is where we want to talk about these particular dynamics and what kind of things we see. A couple of things to start with. One is that we know that the time constant will be typically the product of the inductance and the capacitance, is what we're going to find for all three of these cases. Well, given we're going to also look for values of L at 200 millihenries and the capacitance of 125 picofarads, that's going to end up giving us a tau that's going to be roughly about 0.16 milliseconds, which ends up giving us a center frequency at 1 kilohertz. It's kind of a nice number when you want to make plots and look at things, and so those values were chosen to make sure we have a reasonable place. The other thing is that we're going to be caring about is the quality factor. And one of the things that comes out in the quality factor is the square root of L over C. And this is actually in units of resistance. And in this case, it's going to be 125 kiloohms. In fact, we'll find out that the Q is going to be related to the R over this quantity. So it's going to be a ratio of resistors. So if you look at this, we're going to be looking at a low-pass filter, a bandpass filter, and a high-pass filter. Now the low-pass filter, you're going to want to be getting things at a low frequency, and at high frequencies it's going to fall off. We're going to see frequency responses, low frequency at about 1. All three of these, the bandpass is going to be at 1. Or the low frequency, the gain region, the place where things are actually passing through, is going to be at a gain of 1. The bandpass will be basically in the middle, and the high pass will be at high frequencies. So this is very useful in terms of the kind of things that we'd see. Now, how do we typically solve all three of these problems? Fundamentally, all of these are basically voltage dividers. And you go, well, wait, I have resistors L's and C. But I know that my capacitance is 1 over SC, and so these two elements are sitting in parallel, and I can get it, and then I have the L, and so I would get that combination, that parallel combination, over the sum, which is the parallel combination plus the inductor. And then you get to go through a little bit of math, and you get a 1 over 1. You get the LC term that comes out. This wasn't just like came from above. It actually comes out of the math and out of the differential equations. And then you actually get this quantity L over R, which is really going to be in the position where I'd have tau over Q. This kind of fits this sort of classic canonical form. And tau over Q, gives me my formulation for Q, and I get the same Q formulation as up there. So this is great. So I can definitely see the low-pass filter structure. Similar thing for the bandpass. I'm going to see the C and the L are in the parallel combination, and I see them those two cases plus the R. And then a little bit of math gives me its equation. Notice the denominator is exactly the same as above, but now I've got S L over R in the numerator. So we're in good shape there, which then gives me a tau over Q and then the tau over Q there. So in this case, it looks very, very similar, except that I just added the S term in the numerator in this case. The high-pass filter is similar, except now I've got R in parallel combination of the inductor, which is SL. Pull this together, and what I find is that I get, in fact, an S squared, tau squared in the numerator, but the denominator term is exactly the same. So that's going to be an LC, that gives me the tau squared, and we're good there. And so the math is great. Now, the thing that you may not realize is you go, well, what does this look like in the magnitude response? You could also ask, what is the phase response? Phase response will be a different conversation. But looking at the magnitude response, which would then be, I would take the S, and the S would then become, which is the Laplace term, goes to j omega, which is saying I'm only dealing with the imaginary parts. And then once I put that in, I could then sort of solve for that absolute value of that magnitude. Okay, pretty good, right? And so if I look at the plots for this and plotted this for 7 different values of Q, and what was those 7 different values? Well, it turns out you look at it for 7 different resistors values. One being at 1.25, which is where Q is 1, where Q is, I'm still going, where Q will be 1. Where I'd say 625 is where Q is a half. And remember, Q is a half is where I've got two real identical roots. So that's kind of a critical point when I'm looking at these curves. And then I'm going to go all the way down to where Q is basically 1/8 to work, and then Q is 8, and that's at 10 kilo ohms, and then 156 is basically the 1/8 case. So I've got that 312, 625, 1.25K, 2.5K, 5, and 10K. And what you notice is some very interesting properties, and I just kind of want to walk through them briefly. So Q of 1/8, 1/4, 1/2, 1, 2, 4, and 8. Notice that for one of the things right at the center frequency, you can actually tell, and as you would expect, that that magnitude would be Q over J. So basically, when you take the magnitude, it's just Q. And what you find is that when you're looking here at 1/8, it's basically going to be, it's about 1/8 here, right at 1. 1/4, 1/2, 1, 2, 4, and 8. And that gives you a really good indication of what this looks like right at the center. Obviously the gain is 1 here, and then this drops off with sort of an S squared kind of term on this side. Or it follows off with 1 over omega squared on that side. The high pass is exactly the same, just flipped. That I now see flipped around the frequency axis. So now I basically have this goes to 1. I still see where the Q values are. I can see for the Q being 1/8, I can see that it's flat. It has an increase of just J omega, and then everything falls into the J omega squared. So I'll see the fact in 1/8 that I've got double roots. This is really cool to see it in that space, whereas when I get up to about 8, I've actually got everything kind of merging. I've got now this sort of high peak that comes from having the complex roots. And so I can kind of see how this builds up as I go all the way through. Further, then I can also see the bandpass. And the bandpass is quite interesting because it has a symmetric kind of drop. On the one case, it's going as J omega. On the drop here, it's going as 1 over J omega. Okay. And so all of those are very similar, but the starting points are different. So Q equals 1/8 means I've got two real roots, which means I've got a range of about 8 here until it's sort of 3 dB point, 8 here until it hits its 3 dB point. That works great. And so as a result, I can say, okay, this is what I'm looking at for something that's sort of 1/8. And so I've got two widely spaced roots. At 1/4, they've come in by a factor of 2. And so that's actually quite nice. At 1/2, I can kind of see that it's kind of got this sort of broad shape. And at 1 is where I start to see a slight amount of peaking in here. And this gives me a really interesting sense of, oh, something's going on with this bandpass that's just a little bit of that complex roots. On the reverse case, Q equals 8, I see this almost Q peak, very similar to what I see here, but it eventually peaks at 1. I know that the gain at that center frequency is 1, and then I see the peaking fall off. So another way to think about it is imagine these lines go I sort of extrapolate these lines to the middle point. It's going to extrapolate basically to 1 over Q, because I've got to start at a high Q and it works its way down. So I see a similar thing for 4 and a similar thing for 2. It's really interesting to see these plots and to really kind of see the different dynamics that happen out of this. Because once you see it, it becomes very, very clear. And is not only important in circuits, but these second-order dynamics show up pretty much in almost all physical systems somewhere, anywhere I'm dealing with differential equations in one form or another.